Welcome back. In this episode, I'll be talking a little bit about topic modeling, which is a very popular analytical technique in the digital humanities, and a little bit about word2vec, which is a word embedding algorithm. But Jensen is not installed by default with Anaconda, so you'll have to go ahead and install it. So if you don't have it on your computer already, you'll have to use the Conda package manager to do this. In order to do this, all you need to do is you need to open up your terminal and just type conda install Jensen. And what this will do is this will get online and it'll download this package for you. I already have it installed, so I don't need to do that. You might need to use sudo conda install Jensen. And then once you do this, you'll have to type in your password. But that will let you install this. And then you'll be good to go. So the other thing you need to know is you need to have the Mallet jar file put in the same directory as your code is running in. Okay? So once you've done that, you'll be ready to do all the exercises in this particular lesson. So to start off, we're going to import Jensen, NLTK, and OS. And we're going to go ahead and load in the texts that we've been working with up to this point. In this case, we're going to start just with the Sherlock Holmes texts. And I'm going to do a little bit of cleaning before we start the analysis. So I want to lemmatize the text, that is, remove the things like conjugation and pluralization, and make sure that it's a real word. Now, you can remove stop words if you want to. I actually generally prefer not to. Computers these days are fast enough and sophisticated enough that you don't need to worry too much about that. But there is a default stop word list in NLTK which you can use, and I've written it down for you right here, nltk.corpus.stopwords, so on English. So I'm going to go ahead and make a set for the stop words. And I do this because sets are a little faster to operate on than lists. But if I were to actually use these stop words, I would just copy this in here and put it in something like that. But I don't really want to do that, so I'm just going to leave this as an empty set. So what I'll do is I'll create an empty list called refined texts. And this is where I'm going to put the lemmatized and cleaned up text. So I'll just go through every text in this list of Sherlock Holmes texts. And I'm going to go ahead and use the NLTK word tokenizer to tokenize it into individual words. And then I'm going to get rid of the punctuation, and I'll lemmatize it. So what I do is I'll just say, for every word in tokenized, if the word is alnum and word is not in stop words, and because stop words is an empty set, I'm just going to keep every word. I'm going to feed the result of that into this lemmatizer.lemmatize, and this will return to me this nice refined list. And I'll append this refined list into refined texts. Now, one of the really cool things about Jensen is that it's designed to take advantage of very quick running algorithms, but many of these require integers, which means that you can't feed strings into them. So it has built-in functions that will help you deal with this fact. So the first thing you want to do is you want to create a dictionary that transforms all of your strings into integers. And you can use jensen.corpora.dictionary to do this. And I'm going to give it my refined text object and to create a new corpus dictionary. One of the really cool things about this corpus dictionary is you can actually use it to filter your texts really nicely. If you can use the filter extremes method, you can say, don't include any word that occurs less than 5 times, and no word that occurs in more than 70% of the documents. Now, I don't really want to do that because I want to include everything, but you can use this to play with your results to see how it changes it. So Jensen uses Bagofwords vectors for topic modeling because topic modeling doesn't need the context, it just needs which words appear in which documents. So Jensen comes with a nice function attached to its corpus dictionary, or rather a method, which is docked to Bagofwords. What you can do is you can go through every text in the refined text and give it to this dock to bow method. What this will do is this will transform the list of words into a list of tuples where the first item in that tuple is an integer representing the word, and the second item is the frequency of that word within this particular document. And this is this processed corpus variable. And this is what we're going to be running our topic modeling on. Now, you can save this process corpus to file pretty easily using mmcorpus.serialize, and you can just uncomment this line on 59 to do that. And you can reload it in a different file using the code on line 61. But we don't really need to do that because our corpus is small enough that it's going to be pretty quick anyway. But if you're working with a very large corpus, you might want to do this. Now, I might want to run a sanity check just to make sure I can recover the original words out of this corpus. I know that I can, but I'll show you this so we can see what's going on. So what I'm going to do is I'm just going to go through the very first document in this process corpus. But I'm going to go through every item in that document. And this item is a tuple where the first value is, again, that term, the integer representing the term, and the second is its frequency. So what I'll do is I'll take the term itself and give it to the corpus dictionary to get the original word. And then I'll look at its frequency, and then I'm just going to go ahead and append these as tuples to this empty vector words list. And then I'm going to go ahead and print out what does this look like directly from the preprocessed corpus for the first 10 items, and then what are the retransformed items. So I'll go ahead and I'll run this Python 23 Jensen 1. And we can see that the process corpus, it takes a second sometimes. The process corpus looks like this. So we have an integer 0 and its frequency 1, 1, 2, 1. And we can see that this is 10, 16A, 27, and so on and so forth. So we know that this is actually working just fine. So let's go ahead and actually run a topic model. So what I'm going to do here is I'm going to go into the next script and take a look at what's going on. So most of this is exactly the same until we get down to here, the process corpus. So we have this cleaned and refined text. What I want to do is I want to run a topic model. Now, the first thing I need to do is I need to decide how many topics I want. And this is not necessarily an easy thing to do. The larger your corpus, the more topics you often have reflected. So you'll have to play around and run it a number of times with fewer or more topics to see what results you start to get. If you have a lot of topics that seem very similar to each other, you need to have more topics. If you have very few numbers of topics, but the topic content seems to not be very similar, it seems to contain a lot of different types of concepts, you'll need to up your number of topics. But if you have a huge number of topics and you seem to have many duplicate topics or very similar topics, you need to reduce the number of topics. And there are mathematical ways of optimizing this, but it's often just easier to run it with different numbers of topics until you get a good balance. Now, we're going to be using technically the latent Dirichlet allocation algorithm to do our topic modeling, and this is one of the most popular ones. And many scholars like to use the Mallet implementation of this. And fortunately, Jensen actually has a wrapper for Mallet. Because using Mallet, you can run it from the command line. It is a command line tool developed by scholars at UMass Amherst. But we can do it from within Python, and this makes dealing with it a little bit easier. You will need to have Java installed on your system and to have downloaded Mallet from this address right here. And you can unzip the resulting download and place it in the same directory as your code. So once you've done this, we actually need to tell Python and Jensen where Mallet lives. If you've, for example, I've downloaded the Mallet 2.0.8 version. You might have 2.0.9 by now. I'm not sure. What I need to do is I need to join this together with the bin, which contains the binary files, and Mallet. And I'm using os.path.join. That way this code works on both Mac, Linux, and Windows computers. Then I'm going to actually train the model. So what I do is I use this jensen.models.wrappers.ldamallet.ldamallet. Don't worry too much about this. If you're using this code, you're all set. So we need to give it a few things. We need to give it the path to where the Mallet binary lives, which we have defined right here on line 51. We need to give it our processed corpus, which we've created up in the code above. For ID to word, we give it that corpus dictionary. That way it can go back and look what words those integers are. We give it the number of topics we want, which here on line 42 we have set to 20. We set the optimize interval to 50, and you can play around with this number, but you get better results when you set this to something. And then we give it a prefix. And here I'm just saying my. This prefix can be any string you want. And this is saying if you want some output files, which we most definitely do, what do you want those to start with? And here I'm just saying my. Then what I can do is I can say, I'll go ahead and from this LDA model, show these topics and the top 5 words in all of these topics. And then what I'll do is I'll just go through each of these topics and I'll print it. Now, this particular part you don't need to worry too much about because we're actually going to be working with the output files more than these lines right here. We're just going to do this so you can kind of get a sense of what that looks like. So we'll go to our terminal. But before we run this, we should double check that we in fact have Mallet installed in the right place. So I'm just going to go ahead and go in here, and I'm going to go into my Hacking the Humanities folder here, and I have already put Mallet inside the same folder with all of my other files. Otherwise, this isn't going to work properly. So just remember to do that. So now what I do is I'll go ahead and run this code, Python 23 Jensen 2 topic model 1. And I'll run this, and it might take a second to figure out what's going on. But as it runs, it's going to show us the process, which is one of the nice things about using Mallet. So here we can see that it's running through our corpus, and it's developing these topic models for us. And this will take a minute or so to finish up. It's going to run about 1,000 times, and it's refining each time it goes through this corpus. So we'll wait here a second. Now, the reason we're using Mallet instead of the built-in Jensen function that does LDA topic modeling is I've not had much success getting it to give me good topics. And Mallet is very well optimized. And Jensen's very, very good at a lot of things. But for some reason, it seems to struggle a little bit with this. Although, if anybody out there is watching this and is a developer on Jensen and I'm doing something wrong, you're welcome to tell me. So let's go ahead and take a look at these results. We can see that I went through these topics and just printed out the 5 top words. So kernel, machine, hydraulic, carriage, mile is the first topic. Bohemia, importance, nicely, claim, right, and so on and so forth. Father, son, Lestrade, Turner. So here we have names, father, son, so family. Lord, lady, Frank, Lestrade. You can see that names kind of dominate this, and this is common in topic modeling. Sometimes you might want to remove those names. But because I gave it the my prefix, now we have these new files in here, my corpus mallet, my corpus text, my doc topics, and so forth. This contains a lot of information about our topic models that we're going to use right now when it comes to actually visualizing these texts. So let's go over to our code and look at the next file. We'll close this. So now what we're going to do is, now that Mallet has created these files for us, what we want to do is we want to go ahead and open them and do a little bit of visualization. So first thing that we're going to do is we're going to import the visualization libraries that we want. So matplotlib. The first thing we're going to do is we're going to load in our visualization libraries, and we're going to use matplotlib, and we're also going to use Seaborn, which is a nice library that makes things look a little bit more fancy. You'll see that here in a second. So the first thing we want to do is we want to go ahead and load in the information. Now the file myTopicKeys contains information on the topics. So we'll go ahead and load this in, and we're going to split it on each line, and we'll close this. And I'm going to create an empty dictionary to hold my topics. So for every line in topic info, if the line is not blank, we're going to go ahead and split the line into split the line by tabs. And I know that the topic number, that is topic 0 to 19, because we had 20 topics, is the first item. The second item is the topic weight. And the words themselves are going to be in the third column in this file, and it's just going to be a list of, I think, the top 20 or so words separated by spaces. So we'll go ahead and break these apart and save them as words, and I'll save this information, topics, the topic number, weight, and words. So now we have all this information in a nice dictionary, and I can look at the first topic by printing topics 0. So we'll print that out, but we're also going to do a little bit of visualization here. So I want to visualize the weight of every topic in this corpus as a bar chart. So what I'll do is I'm going to use SNS, which is Seaborn, so I've imported Seaborn as SNS, and I'm going to use the .set method. So this is just going to set our matplotlib aesthetics to the default Seaborn aesthetics. And this makes it look a little bit more contemporary. Now, because it's a bar chart, you might remember from the visualization lessons that I need an index. So I'm just going to say I for I in range of the length and topic. So this is just 0 to 19. Then I'm going to get the topic, or the weight of each topic in order. So I'm just going to go through all of the topics and get them out of that topic's dictionary and get the very first item, which is the weight. Then what we're going to do is we're going to create some labels. So topic I for I in range, the length of topics. And here we're just using F strings to do that. Now we could do I+1, so we have topics 1 to 20, but I'm not worried too much about that. So then what I want to do is I want to give the Seaborn barplot function the index and the weights. And then I want to label the xticks with the labels, and I'm going to set the rotation equal to 90. And then the x label topics, y label weight, title is topic weights, and we'll use that type layout function. And then we're going to go ahead and show it. So let's go ahead and run this. So this is 23 Jensen 2, topic model 2. And we'll run this, and we'll see this nice, pretty bar plot with all of our topics. And we can see that topic 5 is much more common in this corpus than any of the other topics. And you can see this looks a little bit nicer than the standard matplotlib bar function, bar plot, excuse me. So let's go ahead and look at the next piece of code in which we visualize the weight of each topic in a particular document. So if you look at the next piece of code, topic model 3, we can see that this is essentially the same thing, only now we're plotting something a little bit different. So to visualize the topic distribution in a single document, I need to look at the data that's contained in the my.topics file. This will contain, for every document in your corpus, the weights of each topic. Okay? So what I'm going to do is I'm just going to go ahead and load in the titles, but I'm going to go ahead and load them in a specific order that I'm going to save in this short titles list. That way, every time I run this, the results look the same. I don't necessarily have to do this. I could just get the short titles out of this dictionary, but then they would be in a slightly different order every time, and I need to make sure that they're not. So what I'll do is I'm just going to open up this my.topics file and load this information out. And I'm going to split it using the split/t, which we saw in the last piece of code we just looked at. And I'm going to save the document topics according to the title. So for the first item, the title might be Twisted Lip. And I'll say for the weight in info2, and so on. So we don't need the first 2 items in that file. They're not the topic weights. So I just want to say for weight in the rest of these items, return the weight as a float. And we do this because this method of loading in the data will actually return it as a string, and we need to make sure that it's not a string. So what I need to do is I'm just going to go ahead and print out the document topics for Twisted Lip, and then I'm going to plot the weights for the man with the twisted lip using the method that we saw in the last piece of code. We're just going to make a bar plot out of it. I'll go ahead and I'll run this. I'll say Python 23 topic model 3, and we'll run this, and it'll go ahead and print out the topic weight for this particular text. But then we can see here it looks like a nice bar chart. So we can move on. We can look at the next piece of code. So let's go ahead and plot the topic distribution for every document, except instead of having each document in its own plot, we're going to put them all together, and we're going to use a stack plot to do this. This does require a little bit of extra data munging, but it's not really that difficult. So what we're going to do is we're going to go ahead and load in this information exactly like what we saw. In order to plot this, we're going to need to know the total number of topics for later. Now, we do know that it's 20 because that's what we ran it as, but it's not a good idea to put that number directly in this piece of code, because if we forget and change it to 25, it'll break this code later. So here we're just keeping track of it by checking the length of the number of data points in this list. So to actually do this, we need to do a little bit of data munging. We need to rearrange it so that each line, instead of having a single document's information, will have a single topic's information and the weight in every document. Okay? So what we'll do is we'll go through our document topics here by title, and we'll get the weights for that particular document. Then what we do is we go through every item in that weights list, and we'll enumerate. So we'll get an index number, and we'll get the weight itself. Then in this doc weight per topic list, what we'll do is we'll find the ith item. So for item 0, which is the first topic, what we'll do is we'll go ahead and append the weight. And then for the next topic, which is topic number 2 at index 1, so that's the second list in this list, we'll append the weight. And we'll do this for all 20 topics. So then the first item in each of these lists, once we're done, will be the weight for that topic from the first document. Okay? It's a little weird, but we need to arrange it this way so the stack plot actually functions properly. Once we've done that, and you've gotten your head around it, we can actually make the plot. So we need an index, we need labels, which is just going to be topic I, and then we'll put the index, the topics, and the labels in the stack plot. And then we'll give it the X-ticks, which are going to be our titles. And then we'll do the legend, type layout, and show. And I'll go ahead and run this now so you can see what this looks like. 23, Jensen, topic model 4. So we'll run this, and it looks like this. Okay? So what we have here, and of course this is very messy, and you wouldn't necessarily want to do this in the real world, is a plot where you have the engineer's thumb, red-headed league. So each of these points, each of these places along this x-axis represent a single document, and each topic in that document is represented in the stack plot. The problem with this is this is not continuous data. There is no reason that the engineer's thumb should be here and red-headed league being next, other than that's how we calculated it in the first place. It could be in any order, so this gives the impression that this data is continuous, and it shouldn't be. These should be discrete plots that are not connected with each other. So in this particular case, a stack plot doesn't make sense. Now, a stack plot would make sense if you were topic modeling every issue of a magazine or a journal. And there's actually a really great example of this about the feminist scholarship journal Signs. And Signs at 40 did something very similar to this, and I encourage you to check that out. I'll put a link in the description of this video. But what we actually would want to do is we would want to make a stacked bar chart to do this, which doesn't give this faulty impression that this is continuous data. So to do that, we'll look at the next piece of code. And I'll close this. OK, so we still have to do a little bit of weird rearranging here, but it should be a little easier now that you've kind of got a sense for how to flip data around its axes. So most of this looks exactly the same. We're loading the data in. We're creating this doc topic per weight. But then what we need to do is we need to make a stacked bar chart. By making a stacked bar chart, we can actually plot the ratio of each topic in every document in a single chart and make it not look continuous, but we're going to have to do a little bit of math first because there is no stacked bar chart function built into matplotlib or Seaborn. So we're going to have to actually calculate where on the y-axis each topic should start. Because the first topic will always start at 0, because that's the baseline, but the next topic needs to be stacked right on top of that, so it should start at the top of the last topic. So we're going to have to do a little bit of math here. So what I'm going to do in order to calculate this, I want baseline information for every topic. That is, where for each document does each topic start? I know that the very first topic should all start at 0, so what I'm doing is I am creating a NumPy array full of zeros that contains 1 0 for each title in the corpus. And I'm going to put that inside of a list because I'm going to want this baseline information for every topic. But I'm going to start with topic 1. And I'm going to use these baselines to remember where each topic should start in terms of the bar chart on the y-axis. This cumulative NumPy array is going to let me calculate these things and build up as I move forward. Okay? So what I'm going to do is for the weights in document weight per topic, I'm going to go ahead and I'm going to turn that weight list into a NumPy array. Okay? And these weights, remember, are the weights of a particular topic within a document. So I'm going to add them to the cumulative list. So for topic 2, in every single item, and I'm going to add them to this cumulative list. So the very first time that I start this, cumulative is this NumPy array of zeros. After I look at the first topic, what it's going to be is the value of the first topic's weight. And then I'm going to append this NumPy array as a list to this baseline list. The second time through this, we're going to be looking at topic 2. And what I'm going to do is I'm going to go ahead and look at topic 2's weight and add it to topic 1's weight. And then I'll add that to my baseline list. Then I'll do topic 3, which adds to topics 1 and 2. Then topic 4 will add to topics 1, 2, and 3, and so on and so forth. And this will give me the baseline level for each topic for each document. Now, I'm going to remove the last baseline because this should all just be 1s by then, and we don't need to start any bars at that point. Then what I'm going to do is I'm going to use our Seaborn to make this look nice. And then what I'll do is I'll go ahead and go through the document weight per topic, the baselines, and the labels. And I'm going to use all of this information to generate my plot. So what I can do is I can say, create a bar plot for each index. And so I'm going to create a bar plot. This is the index, which is just 0 to however. So I'm going to use the index, which is just 0 to however many documents I have. I'm going to give it the doc weights. So this is the weight of topic 1 in all of the documents, the weights of topic 2 in all of the documents, and so on. And I'm going to say bottom equals baseline. So the bottom is going to be 0 for everything the first time around. But then the second time around, the bottom is going to be wherever the first topic ended. And then I'm going to give it the labels. I apologize, this is a little confusing, but hopefully if you look at the code and think about it, it will become clear. And I'll go ahead and I'll run this. And I'll say Python, let's see here, Jensen topic model 5, and we'll run it. And here we can see that in fact, now we have a stacked bar chart. So this is a really nice way of visualizing these topics. Now, this is actually not necessarily a great example because there are so many topics that certain colors are recycled. And this is one of the default color palettes in Seaborn. Now you can play around and try to create a color palette that doesn't have any repetitions, but this is going to get more and more difficult the more topics you have. So don't worry too much about it, but visually this may not be the best way of interpreting it. But now you know how to actually do it. So now you know how to actually build and run a topic model and a little bit about how to visualize it. Now, interpreting topic models is actually a little bit difficult because there are open questions as to what a topic is in a meaningful sense. It is technically a probability distribution across words. But when we put that in a humanities context, what do these topics tell us about a particular document? We'll get into that more in class, and I will have other videos that go into detail about this in topic models. The other question is, what are these topics? How do we know what topic 1 is? Well, ideally, you should go into the topic and look at the words and try to come up with some sense of what this topic means. Now, this is a little loosey-goosey, and it's not necessarily very scientific, but it will help you really understand the larger shape of corpora that you're working with if you want to do this. But like I say, that's something we talk a lot about in class and is not necessarily the purview of these technical tutorials. The last thing I want to talk about when it comes to Jensen really quickly is word2vec. Now, word2vec is a really nice technique that has been very hot recently, where it will essentially take context into account to give you mathematical representations of words. And this will let you do math on them. The very interesting canonical example is looking at, you're able to essentially take the vector for king, subtract out man, add in the vector for woman, and ideally the resulting vector should look very similar to the vector for queen. We'll talk a little bit about how to do that here in a second. So let's take a look at the last piece of code in this lesson, the Jensen word2vec. Now, word embedding models are a really popular tool these days, and Jensen has a very good implementation for the popular word2vec model. Now, essentially what these are doing is these are trying to develop machine learning models that let you predict a word from its context, or alternatively, the context based on a word. And it turns out that this will let you actually build up useful mathematical representations of words in your corpus. The canonical example is if you have a large enough corpus, you can get a vector for king, and then from that vector, you can subtract out the vector for man and add in the vector for woman, and what you'll get is a vector that looks a lot like queen. And this is a really useful thing to do for exploratory humanistic analysis as well. So what we're going to do is we're going to load in everything in basically the same way, except word2vec actually wants tokenized sentences. So we're going to be breaking our documents apart in a slightly different way than what we've done before. So I have this empty refined sentences list, and I'm going to go through each text in Sherlock texts, and I'm going to tokenize it into sentences. And then for each of those sentences, I'm going to go ahead and filter it. So I'm going to remove words that are punctuation, and I'm going to go ahead and lemmatize things. And so what I have is a list of sentences in this corpus that are then tokenized into refined words. And then I can just feed this refined sentences list straight into the Jensen model's word2vec model. And this will train a word2vec model for me, and then I can start to do some cool things with it. I can look at vectors for individual words, so I can get the vector for Sherlock if I want. I can check similar words using wv.mostSimilar, so I can see what's the most similar to the word him. And I can actually print close to him is similar to him. And I can also perform math on these vectors. So I can get most similar, and I can do positive equals man and gentleman, and negative equals man. So what this means is I'm going to add the vectors for woman and gentleman together and subtract out the vector for man. And this will give me a list of vectors that are similar to that. So I'll go ahead and I'll run this. It's Jensen 3, 23, Jensen 3, and we'll run this. And it'll take a second to train the model, but because it's a small corpus, it won't take that long. But that also means that the results are not necessarily that clear. So here, what we can do is we can see this list of words is most similar to him. Now, in some cases, this doesn't make much sense, but son does. And this is just because it's a very small corpus. And we can see woman plus gentleman minus man is yourself, here, your, sir, give, and so on and so forth. So this is a really nice way of looking at the relationships among words and trying to figure out how they operate in different contexts. So that's just a quick taster of word2vec, and I hope you are interested in learning more about it. But for the context of this class, that's all we're going to have time to talk about. In the next episode, we're going to be talking a little bit about how to get data from the web. So I hope you'll join us next time. Thank you.